Howdy everybody. In this lecturette, we're going to practice taking derivatives. But pay close attention. There's three things that I have to tell you. Let's start with a geometric problem. Let's find where the graphs of this function, f of x equals x to the fourth plus 5x cubed minus 20, and g of x, which is x cubed plus 20x squared minus 20, let's find where these two graphs are parallel. So, as we know, the derivative of a function at some point x gives you the slope of the tangent line. That's a reasonable notion of the slope of the function itself, since the slope of the function and the slope of the tangent line are the same. Well, two lines are parallel precisely when they have the same slope. So that means f of x and g of x are parallel precisely when their derivatives are equal. Because that means that they'll be pointing in the same direction. Their tangent lines at those 2 points will have the same slope. Now that doesn't mean that they go through the same point. For example, suppose this is f of x, like that, and then g of x is something like this. Then the two functions are parallel about there. See what I mean? The tangent lines at that point has the same slope. So we're looking for something like that, some point where the tangent line has the same slope, even though it's not going through the same point. Okay, so in order to solve this problem, we need to compute the derivative of each function. And I'm going to use the d by dx notation, and I'm going to use our rules for taking derivatives. No more limit of the difference quotient. So to take the derivative of this sum, we can take the derivative of each piece and add them together. And then the derivative of each piece is given by the power rule. The derivative of x to the fourth is 4x cubed. The constant 5 doesn't affect the derivative. We then bring down the 3 and subtract 1 to get 3x squared. That's getting multiplied by the 5. And then what's the derivative of minus 20? Remember, the derivative of any constant is 0. So the derivative of that term just gives you 0. And so we get 4x cubed plus 15x squared for the derivative of f. Alright, next up, let's find the derivative of g. The derivative of g is the derivative of x cubed plus 20x squared minus 20. And again, I'll use the power rule and the fact that we can just take the derivative piece by piece and add them all up. So here the derivative of 20x squared is 20 times the derivative of x squared, which is 2x. And again, the derivative of minus 20 is 0. So for g prime of x, we get 3x squared plus 40x. Excellent. So remember, we're trying to find where the two graphs of these functions are parallel. They're parallel when the derivatives agree. So that means we need to solve for x in the equation that says that the derivatives are equal. If we can find when this equation holds, we'll know when the derivatives are equal. So we just set these two derivative functions equal to each other and solve for x. We have 4x cubed plus 5x squared, and we're going to set that equal to 3x squared plus 40x. Alright. Well, to solve for x, let's move the right-hand side over to the left-hand side. Then we'll have a 0 on the right-hand side. we subtract 3x squared from both sides, so subtracting 3x squared from 15x squared, we get 12x squared, and then subtracting 40x, we get minus 40x. And that's all equal to 0. Okay, we're almost done. We just need a factor to find the solutions. Looks like we have a common factor of 4x on all the terms. So what's left after we factor out 4x? X squared plus 3x minus 10x. That's equal to 0. And so finally, the complete factorization is 4x times x minus 2 times x plus 5. That's equal to 0. So we see that the answer is when x is equal to 0, 2, and minus 5. Those are the x values where the two graphs are parallel. We're going to take the derivative of this function, 2 over t to the 4th minus the 4th root of t over 81. Now remember, the d by dx, or in this case d by dt notation, that just means take the derivative with respect to that variable there in the denominator. So in this case, it's not d by dx, it's d by dt. That just means take the derivative with respect to the variable t. That's all that that means. So again, we're going to use the power rule. Let's first write each piece as a constant times a power of t. For the first piece, that would be t to the minus 4, because 1 over t to the 4th is the same thing as t to the minus 4. For the second piece, we need to be a little bit more clever. First of all, I'm going to separate the 4th root of t and the 4th root of 81. Remember, roots of a fraction are just the individual roots of the numerator and denominator as a fraction. I can rewrite the 4th root of t over 81 as the 4th root of t divided by the 4th root of 81. Okay, we'll leave that alone for a second and work on the first part. What's the derivative of this? Well, we have the constant 2. The minus 4 comes down, and then we subtract 1 from the exponent. Always remember to subtract 1 from the exponent. That's what the power rule says. Okay, what's going on over here? Well, we can actually recognize the 4th root of 81 because 81 is a 4th power. Do you know what I'm talking about? You probably remember that 9 squared is 81, but since 3 squared is 9, that means that 81 is 3 to the 4th. So in fact, we can rewrite that function. I'll write it in steps here. It's 1 over the 4th root of 3 to the 4th. I'm writing the constant as its own fraction out front. And then I'll write the function of t as just t to the a. In this case, a is 1/4. That's the same function right there. Continuing along, we have minus 8 times t to the minus 5. And now we're ready to take the derivative here. First of all, the constant comes out. Since we're taking the 4th root of a 4th power, it is just that number 3. The 4th root of 81 is 3. And then we need to take the derivative of t to the 1/4. Let's see, the 1/4 comes down, and then we subtract 1 from the exponent. There you go. So that's the derivative. Let's make it look a little nicer. It's minus 8 times t to the minus 5 minus 1/12 times t to the 1/4 minus 1. That's minus 3/4. And let's just leave it that way. That's fine.
I will tell you 3 things. If I tell them to you, when they come true, then will you believe me? The first thing I will tell you is,
it's time to find the derivative of some new functions. Using the power rule, we've been able to take the derivative of a lot of functions, especially equipped with these basic rules. But what do we do about the trig functions? Sine of x is not a power of x. It doesn't look like x to the a. So what is its derivative? We're now going to find the answer. First, an important note, we will always use radians for our trig functions instead of degrees unless stated otherwise. It just makes the formulas a little bit nicer. There would be some constants involving 360 and 2 pi that we would have to put in if we wanted to use degrees. So we're going to be using radians for our trig functions. Okay, how are we going to find the derivative of sine? We can't use the power rule. We can't really use any other rule. So we have to go back to the definition of the derivative. It's time to compute the limit of a difference quotient again. So the definition of the derivative of sine of x is the limit as h goes to 0 of the change in y from x to x plus h, so that would be sine of x plus h minus sine of x, divided by the change in x, which is just h. And now in order to evaluate that limit, there's no algebraic tricks we can immediately do. There's no h that we can factor or anything, right? So instead, we're going to use the sum formula for sine. The sine of the sum of two angles, such as x plus h, is given by the sine of the first angle x times the cosine of the second angle h plus the cosine of the first angle x times the sine of the second angle h. So that whole term in parentheses there, that is sine of x plus h, using the sum formula for sine. The minus sine of x, that's just going to hang out there and stay the same for now. We still can't factor out an h, but notice that there's a common term of sine of x. So let's take that sine of x and factor it out from the parts that have a sine of x factor. That would be the cosine of h term, and then minus sine of x means we factor out a minus 1, like that. So I just factored out sine of x from cosine of h and from minus 1. Okay, there's no sine of x here, so there's nothing else that we can do there. So for this next piece, we're just going to leave it alone, like that. Okay, very good. Now, remember, we can always split a limit of a sum like this. This is a sum of two fractions. We can split it up as the limit of the sum of each individual piece, provided they exist. So as long as the limits that I'm about to write down end up existing, we're going to be okay. So the limit of the first piece, the first term over h, would be sine of x times cosine of h minus 1 over h. And then the second piece is cosine of x sine of h divided by h. Like that. We have to be very careful about distinguishing x and h here. And now here's the crucial step. Sine of x, that's constant as a function of h. It does not depend on h. So it passes through the limit. It's behaving just like 3 or negative 10 or something. We can rewrite that first limit as sine of x times the limit as h goes to 0 of this fraction involving cosine. Like that. Similarly, cosine of x does not depend on h. So we can pull it through the limit. Again, this is cowboy mathematics. All of these computations are valid, provided that at the end of the day, the new limits that I'm writing down actually exist. Oh, whoa, 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 you guys, check it out. Holy moly. Do you recognize this? That's our old friend. We've been talking about that limit for weeks now. This is that funky, funky limit, the limit of sine over the variable. Usually we were writing it as sine of x over x, but that doesn't matter. We're taking the limit as h goes to 0 of sine of h over h. All right, and what was that limit? That is equal to 1. We've seen that limit before. All right, that's a very, very special limit, and it's useful here in this computation. It turns out that this other limit, cosine of h minus 1 over h, is a similar sort of special limit. You can evaluate this one numerically and figure out that this limit is 0. So at the end of the day, because these two limits exist, we get sine of x times 0 plus cosine of x times 1. And so, what have we shown? We've shown that the derivative of sine is just cosine.
Second thing is...
We just saw that the derivative of sine of x is cosine of x. Amazing, amazing fact. It turns out that you can do a similar calculation using the definition of the derivative to see that the derivative of cosine is minus sine. So the derivative of sine is cosine, but the derivative doesn't go in the reverse direction. Instead, it takes cosine to minus sine. The derivative of minus sine, because that minus sign, we can think of that as just a minus 1, that comes through. It's just the opposite of the derivative of sine, so it's minus cosine. And similarly, the derivative of minus cosine is sine. So these are 4 fundamental derivatives. You should have these completely memorized. These are really important. I like to remember these derivatives in the following way. I draw a little circle. I have sine of x on top, and I'm going to go through these 4 functions sort of like going through the clock, if you like. And each time I write an arrow, that arrow just means d by dx. It means take the derivative. So the derivative of sine is cosine, so sine is taken to cosine. The derivative of cosine is minus sine, so cosine swings down to the bottom of the circle at minus sine. Over here we have minus cosine, and the derivative of minus sine is minus cosine. And then finally, completing the circle, the derivative of minus cosine is sine. So if you remember that the first step of the circle takes sine to cosine, and that then you go back to a sine but with an opposite sign, you'll remember that you're going through these 4 functions exactly once before you get back to sine. So if you keep taking the derivatives of these functions, you'll be going in a circle over and over and over and over. The derivative operator here has sort of a symmetry of order 4. Going through the derivatives of these trig functions, you get back to where you started every 4 times you take the derivative.
Think of me as a friend.
Okay, next up we're going to find the derivative of a function that's built up out of trig functions and a power of u. Here the variable, the input variable of the function is u instead of x, just for fun. So we're taking cosine and sine and we're cubing the variable u, and we'll do the usual game, taking the derivative with respect to u. So what is it? F prime of u, the derivative with respect to u, is given by taking the derivative of each piece individually. So we're starting to get the hang of this. So I'm going to not show all of my steps. For the derivative of the first function, we have 3 times cosine of u, and that 3 will come through the derivative operator. It's just 3 times the derivative of cosine of u. Next up we have minus the derivative of sine of u. And then for the final piece, we're taking the derivative with respect to u of 5 times u to the minus 3. 5 over u cubed is the same thing as 5 times u to the minus 3. What do we get? Well, we now know the derivative of sine and cosine. The derivative of cosine is minus sine. The derivative of sine is cosine. And then for the final piece, we use the power rule. The 5 comes through, that's just a constant. We bring down the exponent, minus 3, and then we subtract 1 from the exponent. So when the dust settles, we get minus 3 sine u minus cosine of u minus 15 u to the minus 4. That's the derivative.